Okay, so welcome back, and we will now start with an example of Simplex. I'm going to give you a complete example without the initialization part, of course, which is going to be the next upcoming video. And this is a complete example with visualization. So we are going to go over the Simplex method on an example. Let's do it. Okay, so let's start with a linear programming problem. I'm going to keep it simple, and I'm going to keep it two-dimensional. So there are two variables in this linear programming problem, x1 and x2. Okay, we are asked to maximize x1 plus 2x2 subject to these constraints here. I'm not going to read them out, but I'm going to show these constraints visually. This is a drawing of the polyhedron. That's the feasible region. So the feasible region is right here. Okay, so if this is the feasible region, and the constraints you can see translate into hyperplanes. So this plane, or this straight line, since it's two dimensions, is this constraint here, right here. Okay, x2 less than equal to 11, that's this constraint right here. Okay, x1 minus x2 less than equal to 3, that's this constraint. x1 less than equal to 6, that's this constraint. So each of these inequalities forms a side, and these two sides come from the non-negativity constraints that we assume in a standard form. Okay, so that's going to be the problem, and this is the visualization. Now you can look at the vertices of this polyhedron. So there's going to be many vertices. So here's one vertex: 0, 0, 3, 0, 6, 3, 6, 11, 3, 11, and 0, 2. So there's 6 vertices of this polygon, and we'll see how Simplex algorithm plays around with this. Okay, so all right, let's get started then. First step is to add slack variables. We've seen this before. Okay, so we are going to add slack variables, and in this case slack variables are x3, x4, x5, and x6. Every inequality gets a slack variable, and the less than equal to gets converted to an equality. Furthermore, all the slack variables become non-negative. So this is just a problem transformation that's added x3, x4, x5, and x6, and these variables are now non-negative. All right. So what have we done with slack variables? Geometrically, we have now created a 6-dimensional problem on the space of x1, x2, x3, x4, x5, and x6, and unfortunately the screen here has just 2 dimensions. So I cannot draw it on the screen, but you can visualize 6 dimensions somehow, and if you visualize the shadow of this problem on just the x1, x2 axis, we retain our original polyhedron. And this is important. The original polyhedron is just the shadow or the projection of this 6-dimensional object that we have created on the x1, x2 axis. And what that means is that we have not changed the nature of the problem by introducing slack variables. That's what we mean by saying that the shadow is just the original polyhedron. Okay, so that's just for visualization. Everything remains the same in spite of adding the slack variables. The problem has not changed. All right. Then the third thing we remember is coming up with the initial dictionary. So the initial dictionary is now going to have the newly introduced slack variables x3, x4, x5, x6. Very conveniently, they are going to remain on the left-hand side. And x3 is going to become 2 plus 3x1 minus x2, which is just this expression going on to the right-hand side. Okay, so do that to x4, x5, x6, and we have formed the initial dictionary. Z is the objective row. So Z is the objective row, and the current objective value is 0. Okay. Having said all of this, let me ask you a question. Where did these constraints go, the non-negativity constraints? And if you recall from the previous videos, these constraints are implicit. We keep them in our mind when we draw a dictionary, but we don't write them out in a dictionary. Okay, so the non-negativity constraints are in our mind, and we just keep them there. All right. Okay, so what's the solution associated with this dictionary? So we all know that every dictionary stands for a solution. What's the solution? Well, the solution is obtained by taking the two non-basic variables, x1 equals 0, x2 equals 0, and that's the rule. Any variable that's in the non-basic row or non-basic column, you make it 0, and everything else gets fixed. So once these two have been made 0, x3 is 2, x4 is 11, x5 is 3 and x6 is 6. Okay, so the x1, x2 part of the solution is 0, 0. Okay, so which means that the current dictionary is looking at this vertex. Okay, the solution associated with this dictionary is this vertex of the polygon. Okay, so we are going to see this connection. Every solution that's associated with the dictionary will be a vertex of the polygon. We are not going to do much about this connection just right yet, but when we get to the topic of geometry of simplex, we are actually going to do this. We are going to study the geometry of polyhedra using simplex. But right now it's too premature. I'm just giving you a flavor of what simplex is doing. Okay, so now it's time to do entering and leaving variable analysis. What are the possible entering variables for this dictionary, and what variables will leave corresponding to the entering variables? Let's recall the rule for entering variables. So entering variable needs to be chosen from here, and the corresponding coefficient +1 and +2 must be greater than 0. So according to my entering variable analysis, x1 can enter if you wish, or x2 can enter. Okay, so let's do the leaving variable analysis by choosing x1 as the entering variable. So assume x1 is chosen to be the entering variable. What variable will leave? Okay, so we can do the leaving variable analysis. Let me erase to make space for it. Okay, so since x1 has been chosen to be the entering variable, we can ignore this column. x2 does not play any further role in this analysis because it's currently fixed at 0 and it's going to remain 0. Let's talk about x1. So suppose I increase x1. Okay, I start from 0 and I increase it. What are the constraints placed on it? So x3 is going to increase. So this does not place any constraint on the increase of x1. x4 is also going to increase and therefore places no constraints. So these two cannot be leaving variables. x5 is decreasing, and in fact this gives us the constraint that x1 less than equal to 3. I cannot take x1 beyond 3, otherwise x5 is going to become negative. Likewise, x6 decreases. Okay, so that creates a conflict, and I cannot take x6 beyond 6, or else x6 is going to be negative. Sorry, I cannot take x1 beyond 6, I'll correct myself, otherwise x6 is going to become negative. All right, so you have x1 less than equal to 3 and x1 less than equal to 6. So this guy trumps, x1 less than equal to 3 trumps, x1 less than equal to 6, and therefore the leaving variable corresponding to x1 is x5. Okay, so this analysis was covered in our previous video, and hopefully you have had enough practice with this that what I've just done is not surprising. If it is, then we need more practice, and hopefully this video gives you more opportunities to practice. All right, so if you did the analysis for x1, you conclude that x1 enters and x5 leaves. Alternatively, you can say x2 enters, and if you choose x2 as the entering variable, then you will find that the corresponding leaving variable is actually x3. So you have a choice. You can say x1 enters and x5 leaves, or you can say x2 enters and x3 leaves. And we can go with either of the two choices. Okay. So we will go with the choice x2 enters and x3 leaves. So that's the choice that we are going to make. Okay. And our goal is to compute a new dictionary. How do we compute a new dictionary? Okay, so if x2 enters and x3 leaves, we look at this row. This has both x2 and x3, and we invert this row. So this row can be inverted to say x2 equals 2 plus 3x1 minus x3. So this said x3 in terms of x2. We invert it and we write down x2 in terms of x3. So, and that goes here, x2 in terms of x3. Okay. Now everywhere else that you see x2, you do this substitution. You replace it with 2 plus 3x1 minus x3, and you get new expressions here. Okay, so for instance, you have 11 minus x2, and that becomes 11 minus 2 plus 3x1 minus x3. That becomes 9 minus 3x1 plus x3, and that's this row. x4 used to be 11 minus x2, and now x4 becomes 9 minus 3x1 plus x3. Every row you perform this substitution for x2. Wherever you see x2, you perform the substitution, simplify, and you get your new dictionary, and we are going to call this dictionary D2. Okay. Now notice that the value of z in this dictionary has risen. So originally we had z equals 0, and now we are up to z equals 4. And that's what Simplex is going to do in every step. It's going to increase the value of z because our goal is to maximize z, take it to the maximum it can be, and so in every step we are going to try and increase the value of z. Okay, so as a result, x2 has entered, so x2 goes here, and x3 has left, so x3 comes back here. So therefore in the new dictionary x3 is here and x2 is here. Okay, now let's look at the solution that's associated with D2. So the solution associated is the non-basic variables x1 and x3 are 0. These two are 0. The basic variables x2 is 2, x4 is 9, x5 is 5, and x6 is 6. And z is 4. So this. And for c this. Okay, so that's the solution associated with this dictionary. And if you want to look at x1, that's 0. And x2 is 2, so it's 0, 2 for x1, x2, which are the only variables from the original problem. x3, x4, x5, and x6 are slack variables that we have added to the problem. Okay, so let's look at what this means. So what this means is, and let me use the eraser to erase this picture a little bit better. So what this means is that we are currently at 0, 2. We used to be here, now we have gone one step and we are here. Okay, and this is dictionary D1, the original dictionary, and now this is dictionary D2. The solution associated with this dictionary is this vertex. Okay, 0, 2, 0, 2, 0, 2. Okay, all right, so we have D2. Let's now do an entering and leaving variable analysis of this dictionary. Okay, what about the entering variable? So we look at the objective row, and we see that x1 is the only possible entering variable. Okay, and corresponding to x1, we can do the leaving variable analysis. So we can forget all about this column, and we can say what's the constraint placed by each of these variables on the increase of x1. Okay, and therefore the constraint placed by x2 on the increase of x1 is less than equal to infinity because this coefficient is positive. Okay, likewise x4 places a constraint of less than equal to 3, x5 places a constraint of less than equal to infinity, and from here less than equal to 6, and the winner is x4. Therefore x1 enters and x4 leaves. Okay, so I hope you got this right, and then we can now move on to the pivoting step where we can force x1 as the entering variable to go here and x4 to come back here. Okay, how does that work? All right, so that works as follows. So we have to say x1 enters, x4 leaves. So let's look at this row, which conveniently has both x1 and x4, and this has x4 in terms of x1, and the operation of pivoting just changes these two first of all. So we have to write x1 in terms of x4, so we can say x1 is, so 3x1, take x1 to the right, here is something like 9 plus x3 minus x4. Okay, if that's taken care of, then you immediately get from here x1 is 9 by 3, 3 minus 1 by 3 x4 plus 1 by 3 x3. Okay, so this is the first row that we create by inverting this row in the original dictionary, and we create this, and then wherever we find an x1, here, here, and here, we substitute this expression. Once we substitute it, we get this new dictionary. Okay, and after we have done with this new dictionary, we have that the objective is now gone up from 4 to 25. Okay, So this is all standard. We have been looking at this for the entire hour for this video, and hopefully this part is clear. Now, if that's clear, then let's look at the solution that's associated with this new dictionary that we are going to call D3. Okay? And the solution associated with D3 is x1 equals 3, x2 equals 11, x3 equals 0 because it's here, x4 equals 0, x5 equals 11, and x6 equals 3. And z equals 25. And you can check that the original objective was x1 plus 2x2, and that gives rise to 25. Okay, so where are we in this feasible region? We are here. We started off here, and then in one step we jumped to here, and now we are jumping to here, and that's D3. All right, so what can we do next? So we can look at D3 and do the entering and leaving variable analysis. Now this gets monotonic, so doing this by hand is going to get rather challenging and rather mistake prone. But the hope is that once we understand this process, we are going to code this up. So therefore, bear with me for just a bit while we are just going to code this up later on, and that's going to come up very soon. All right, let's do the same thing, entering variable. x4 cannot be an entering variable, but x3 can. So okay, so x3 is the entering variable. And you can do the leaving variable analysis corresponding to which variable is going to leave. So x1 places no constraint on the increase of x3 because this coefficient is positive. Again, no constraint because this is 0, and therefore it still places no constraint. This places a constraint of less than equal to 11 divided by 1 by 3, and that's 33. That's the level to which it allows x3 to increase. And finally, this places a constraint of 9. So the winner here is x6. So x6 leaves. Did we get that right? And we did. x3 enters and x6 leaves. Very good. Now if that part is clear, then we can do the pivoting, and I'm going to spare you the details this once, okay? And you get this new dictionary D4. Okay, and is this the last dictionary? Maybe, maybe not. We need to do the entering variable analysis again. Let's do the entering variable analysis. So can x4 be entering? No. x6 cannot be entering? No. Therefore, thankfully we are done. We have arrived at a final dictionary. That's D4. Now the objective once again has gone up from 25 to 28, and z star, the final objective, is going to be 28. Okay, hopefully all of this is now clear, and we are now in a good position to program some of this. But let's keep going. All right, so here is the final dictionary once again. Objective value is 28. And where are we? So we are at x1 equals 6, x2 equals 11. So this is the original problem variable, and you can visualize it right here. Okay, that's the objective. And if you look at the level set of x1 plus 2x2, that looks like this. Then it's pretty clear that the objective is this. So once we drew the picture, we always knew that 6, 11 was going to be the optimal solution. Okay, the optimal solution was 6, 11 because the level sets of the objective functions look like these dotted lines. Okay, we knew that, but we wanted to find that out using Simplex, and gives us a lot more confidence that we understand Simplex, and it works very well for us. And the slack variables from the original problem now have values 9, x4 is 0, x5 is 8, and x6 is 0. Did I get that right? Hopefully I did. And you can check my work, and the final answer is 28. That's achieved at x1 equals 6 and x2 equals 11. Very good. So what has Simplex done? So Simplex, as I said, has gone from here to here to here to here. Okay, there's an alternate path. If we had chosen a different entering variable in the first step, then we could have gone this way as well to achieve the same answer. All right. So if that is clear, now let's take a different example and see what happens. And this is by means of a segue into my next lecture. All right. So let's take another example, which is this problem that I have written down below. You don't have to worry about the problem itself. Let's look at the feasible region, which is this this quadrilateral kind of a polyhedron, this four-sided polyhedron here. Okay, and now let's do the whole thing. Let's add slack variables as before, x3, x4, x5, x6. We added the slack variables, and we got to the initial dictionary using the automatic process that we already know. But what is the solution associated with this dictionary? Well, the solution is x1 equals 0 and x2 equals 0. And one odd thing to note about this dictionary is that these two guys, x3 and x4, are negative, which means that the corresponding constraints here are not satisfied. So this dictionary, if you recall, we had a name for this, and this is infeasible. Okay, so starting off, Simplex gets us to an infeasible dictionary, and we don't know how to proceed from here. You can do your pivoting, but you don't go anywhere. And geometrically, what's the picture? The picture is, well, this is your polyhedron here. This is the feasible region. But we are stuck here as our starting dictionary. This is D0. How do we get to some place on the feasible region before we can start our pivoting process? Okay? And the answer to that is a new phase of Simplex that we are going to carry out, and that's going to be the initialization phase Simplex. Okay? In this phase, we are going to carry out the same old Simplex algorithm on a slightly different problem that's going to get us from here to here, or maybe here, or maybe here, or maybe here. It's going to get us to some feasible point on the polyhedron, and from there we can start the Simplex that I covered in this tutorial. Okay, so we are going to see how that works and how to initialize for all problems in the next lecture, and that will complete the presentation of the entire Simplex algorithm with the initialization phase as well.